Support for UWM podcasts comes from University School of Milwaukee, fulfilling a values-based mission of developing learners, fostering leaders, and preparing citizens for pre-kindergarten through 12th grade. More information at usm.org/mission.
Lake Effect brings you conversations about what's happening in Milwaukee and the people, places, and organizations that shape our community. This is Lake Effect Spotlight from UWM, Milwaukee's NPR.
It's been just over a decade since the game-changing discovery of gravitational waves in the distant universe. Gravitational waves are ripples in space-time caused by cosmic collisions. By processing massive amounts of data, UW-Milwaukee scientists played key roles in the discovery, contributing to a Nobel Prize in physics. The discovery of gravitational waves opened a new door of study, and this work continues in our backyard today. To learn more about the significance of this anniversary and the new discoveries it's led to, Lake Effect's Audrey Nowakowski speaks with UWM Physics and Astronomy Assistant Professor Lia Medeiros.
It's been a decade since the groundbreaking detection of gravitational waves. So before we get into its significance and why it's important, let's start with some basics and definitions. What are gravitational waves?
So to understand gravitational waves, we have to understand just a little bit of Einstein's theory of gravity. And what Einstein's theory of gravity says is that we all live in a four-dimensional space, and that is called space-time. So we have three dimensions of space, but we are also moving through time as well. And Einstein's theory really does require that we think about space and time as two parts of the same thing. And what this theory states is that mass can actually curve space-time itself, which I know might sound a little counterintuitive, but what we experience as gravity actually fundamentally is the curvature of space-time itself. And then in turn, the curvature of space-time tells matter how to move. And so the way that I like to define a black hole, for example, is that a black hole is a region of space-time where the curvature is so extreme that nothing can escape, not even light itself. And so when we're talking about gravitational waves, most come from the merger of two black holes. It doesn't have to be black holes, but that's what most of them are. So since black holes curve space-time, if they are spiraling around each other and merging into one bigger black hole, effectively two black holes will collide into each other and create a bigger black hole. As they are spiraling around each other, they effectively drag that space-time curvature that they're creating with themselves as they move, and that effectively creates these ripples in space-time itself that propagate outward at the speed of light. And so we can actually detect these very, very, very tiny ripples in space-time itself. Space actually contracts and expands just ever so slightly, and we can actually detect that.
So from what I'm understanding, gravitational waves, maybe I'm thinking too large scale, it's like the ripples are the waves, right? These little detections that you're picking up from these black holes colliding.
Yeah, so what we actually detect as the gravitational waves is a really, really incredibly tiny effect. What's really funny, I think, if you look historically, is that the scientific papers that were published about gravitational waves originally, even in those papers, they effectively acknowledge the fact that this is an interesting calculation and it's an interesting result, but there's just absolutely no hope of us ever detecting that. It's just a curiosity. And so it's really, really incredible to kind of look back historically and to realize that we have really surpassed the expectations of those scientists so many years ago when they first discovered that the theory of general relativity, Einstein's theory of gravity, predicted these gravitational waves.
Yeah, and it's really exciting to live and see the progress and see it continue on further. So to go back to the discovery, the detection of gravitational waves, how were they discovered and how did UWM play a role in this?
Yeah, so UWM has been really important and really influential in the field of gravitation since the 70s. We've had a lot of really important professors and scientists who worked at UWM contribute really significantly to this field. And so since the 1970s, we had here Leonard Parker, who worked on gravitation, and his work actually laid the foundation for Hawking's theory of Hawking radiation, which is incredibly influential and important. And then in the 90s, we had John Friedman and Bruce Allen, who also really influential and important in the field of gravitational waves. And in the 90s, UWM made a really major commitment to gravitational wave research and hired three additional professors, Alan Wiseman, Julian Creighton, and Patrick Brady, all of whom are still here and very active to this day. And with these new hires in the 90s, UWM was able to build one of the strongest theory groups within the LIGO collaboration. And LIGO, of course, is a international collaboration that detected gravitational waves for the first time, and it has thousands of members globally.
And LIGO stands for?
LIGO stands for Laser Interferometer Gravitational Wave Observatory. And effectively, LIGO is made up of actual instruments here on Earth that are the interferometers, and they detect really tiny infinitesimal expansion or contraction of space-time itself. And through that detection are able to learn a lot about the black holes that actually collided and generated these gravitational waves.
So it's really cool and interesting and widely unknown, maybe unfairly, that we have this massive hub of black hole and gravitational discovery in our backyard, and that UWM is one of the key places for this. You mentioned LIGO. There's also a couple other groupings at the CGCA Center that contribute to this kind of work. Let's address some of that, and starting with nanograv. This is specifically for pulsars. Can you explain the work that nanograv does?
Yeah, so LIGO detects gravitational waves from black hole mergers of black holes that are, maybe on the order of 10 to 100 or so times the mass of the sun. And nanograv uses different techniques and can detect mergers of what we call supermassive black holes, that are black holes that have millions or even billions of times the mass of the sun. And the way that nanograv actually does that is, instead of having a physical instrument here on Earth, they use these really kind of crazy, incredibly compact stars called pulsars. And by measuring the time delay for the light that reaches the Earth from these pulsars, they can actually detect gravitational waves coming from mergers of supermassive black holes. And then more recently, just within 2025, I've also joined the CGCA and joined UWM, and I work on the Event Horizon Telescope. And that's also a global large-scale collaboration that focuses on gravity and black hole research. And what we do is we use a collection of telescopes spread around the world to take images of black holes and also learn more about black holes themselves and gravity through these images.
So this discovery 10 years ago opened a whole new door, a whole new field into gravitational wave astronomy and the wide array of physics to test and have in this hub. So can you share what kind of information gravitational waves and gravity and black holes do they hold that wasn't found in other space objects that makes this discovery so significant and has opened up these new doors?
Yeah, that's a wonderful question. The way that I like to talk about this actually is kind of from my personal experience of how I've grown up within this field. When I started my PhD, I wanted to use black holes in space to test our understanding of gravity itself. And that just wasn't something that humans had ever done before. And the very first detection of gravitational waves happened when I was in the first few years of my PhD. And that really did kind of mark the dawn of a new era of black hole astrophysics. And since then, we have just learned so much about gravity itself, but also learned so much about the kinds of black holes that are out there, what their mass distributions are, how frequently they merge, how they grow, how they evolve. Just so much information. It's really been kind of like night and day before and after these free collaborations that I mentioned earlier came online and had their first detections. So, it's kind of a new subfield of astrophysics that we're all very excited about. And of course, UWM is playing a really, really significant role in this new field. And it really is just, we're effectively using black holes in space as a really extreme laboratory to test our most fundamental physics theories, which again is incredibly powerful, incredibly exciting, and not something that we were able to do just a few years ago.
Could you highlight for me maybe one or two other discoveries that were made possible because of the detection of gravitational waves?
Yeah, so I'll mention a couple things. So, one of the things that's really, really powerful and exciting for us is the fact that we were able to show that gravitational waves travel at the speed of light. Because they travel at the speed of light, it actually is a really powerful constraint on our understanding of gravity itself, and it shows that Einstein's theory of gravity does seem to really precisely predict the reality of the universe. So that's really, really incredible. Something else that's been really exciting for us is the fact that before the very first gravitational wave detection, we had never actually really directly detected a binary black hole. And so when I say binary black hole, what I mean is just two black holes orbiting around each other. And so the very first detection also signified the very first time that we were really able to show that black holes do actually orbit each other, and it is possible for them to merge into one bigger black hole.
It's amazing learning more about black holes because they're always, for the general population, seen in movies, big, ominous things, right? And then the science of learning more and breaking it down, and also the fact that gravitational waves confirmed E equals mc squared 100 years after Einstein wrote it out. As the newest faculty of the CGCA, what are you most excited about? What are you looking forward to in your new role here in Milwaukee?
I'm really excited for a few results that I am currently working on with my collaboration. So we published the first image of a black hole on April 10th of 2019. And then we published the first ever image of the black hole at the center of our own galaxy in 2022. And I was very involved in both of those results. And in 2023, I published an updated version of that very first image. And in that updated version, what I did was I reanalyzed the raw data that we get from the telescopes with a machine learning algorithm. And I was able to achieve effectively a factor of 2 improvement in resolution for that image, which is really exciting. If you're interested, the algorithm is called Primo, and you can find a lot of information online about that. And so what I'm personally excited about is that I'm about to publish a new version of Primo that has a lot of new capabilities, and I hope in the next few years will allow us to have a high resolution movie of a black hole so that we can really see how matter swirls around the black hole and learn a lot more about how matter interacts with the gravitational field of the black hole and how it falls in.
That sounds awesome. I look forward to having you back when you have these updated images to talk more about it. But for today, thank you so much for joining me to talk about the anniversary of gravitational waves.
Thank you so much for having me. It's been wonderful.
Lia Medeiros is an assistant professor at UW-Milwaukee in the Physics and Astronomy Department. She's also a member of the Center for Gravitation, Cosmology, and Astrophysics, also known as CGCA. Medeiros joined Lake Effect's Audrey Nowakowski to talk about gravitational waves. If you'd like to dive into more outer space, the CGCA is hosting an event tonight that addresses the age-old question, are we alone in the universe? You can find more information about the event at wuwm.com.
You can find more interviews like this one by visiting wuwm.com/Lake Effect. And while you're there, subscribe to the Lake Effect Spotlight podcast.